Again, so what we are hoping to do today is to give you an overview of where the field of 21 centimeter cosmology is today, specifically the part of 21 centimeter cosmology that aims to study the cosmic dawn and the epoch of reionization. So as Anthony was mentioning, this will be split in two halves. I will start by introducing the field of 21 centimeter cosmology, the infant universe, cosmic dawn, epoch of reionization, and how do we plan to use radio observations of the 21 centimeter line to study these epochs. I will follow on then with the state of the art in observational 21 centimeter cosmology. What are the experiments that are at the moment piercing through the IGM and trying to do these observations, and I will make a special mention to those that the Kavli is involved with. And then Anastasia will take from there and it will tell us about how to interpret these observations and what can we learn actually about the physics of the early universe from the 21 centimeter line. Right, so I think a lot of us have seen a similar plot to this in the past, but I just want to start by making sure we are all on the same page. So by the infant universe, what we mean is actually these three epochs, the Dark Ages, the Cosmic Dawn, and the Epoch of Re-ionization. This is the goal of our studies, of our research. We are trying to understand, first of all, how did dark matter interact with ordinary matter, provide the necessary conditions for the formation of the first stars, of the first galaxies, of the first celestial objects during the Dark Ages, right after the CMB decouple and before first star formation during the Cosmic Dawn. Subsequently, we want to understand how and when did the first stars form from the basic elements like atomic hydrogen. And then eventually we want to understand how these new lights, new stars, new celestial objects shaped the universe, shaped the intergalactic medium until it became, first of all, transparent to short-wave light, so we can observe it with many types of telescopes from Earth today, and it can show us the type of universe we see from Earth. Right, so the 21 centimeter line, this is how we are going to hopefully get there. Neutral hydrogen, the most abundant element in the universe during its infancy. It has a natural forbidden transition, a 21 centimeter wavelength, which most importantly has a radiation temperature, which is Ts, the spin temperature. And this emission of a photon of 21 centimeter wavelength happens when the configuration of the proton and electron changes from parallel to anti-parallel, which means actually the magnetic dipole of these of the two particles are aligned, and then they are more stable, so they are a bit closer. The electrons are a bit closer to the proton, so there is this 6 microelectron volt emission. Now, it is an emission line, and it redshifts as the universe expands, and therefore we can use it to study the evolution of the early universe if we are able to trace this redshift of the 21 centimeter line. The important thing, the most important thing here is that the radiation temperature of the 21 centimeter line couples and decouples to other temperatures during the infant universe, which is what really allows us to understand, hopefully try to understand the physics of the early universe. Because of different physical processes, it can couple or decouple to the gas kinetic temperature or to the background CMB temperature. And this is really what we try to use to understand better the infant universe. 21 centimeter line is a radiative transfer problem. So what we are studying, as I said, is how this spin temperature decouple from the cosmic microwave background and then couple back to it again throughout redshift, throughout cosmic timeline. So we have three main components again: the background temperature, mostly the CMB, the gas kinetic temperature, and the spin radiation temperature. And what we hope to measure with radio telescopes today is the brightness temperature of the 21 centimeter line, which is this radiative transfer. Very good, so what can we potentially understand and learn from the infant universe? Well, here what we see is that we have this baseline, zero baseline. This is actually the background temperature, mostly the CMB temperature, and the solid line is the 21 centimeter line in this plot, average across all directions in the sky. This is an example 21 centimeter signal. As you can see, it departs from the baseline and it goes back to it across cosmic time. across redshift. And at the beginning, during the dark ages, when the universe was expanding, the gas was cooling down, and because of collisions, we had the spin temperature coupling to the gas temperature, potentially allowing us to see this 21 centimeter line in absorption, until eventually these collisions became less frequent with the continuous expansion of the universe, and the spin temperature coupled back to the background temperature. Then we have the cosmic dawn, birth of the first stars, and Lyman alpha photons from these first stars helped the spin temperature couple again to the gas temperature, which was colder than the CMB. Eventually, this process also saturated. We also had X-rays heating up the gas, and what we can see is the spin temperature going up all the way across the CMB, potentially to a higher temperature than the background temperature, until we had UV photons from the first massive galaxies reionizing the IgM, until the IgM was mostly reionized, so no more neutral hydrogen or very little neutral hydrogen. Most of the hydrogen in the universe was either ionized or in small pockets in galaxies. Right, so what's the challenge? Why haven't we got there yet? Well, the main thing is that the signal we are trying to detect, the cosmological 21 centimeter signal in the order of millikelvins, is buried underneath foregrounds that are up to 5 orders of magnitude stronger. Several types of foregrounds, extragalactic, galactic, even foregrounds here on Earth. The ionosphere is one of the main challenges. All of them, especially synchrotron emission, is up to 5 orders of magnitude stronger, which makes this an extreme observational challenge. How do we clean all of this until we can get potentially to the 21 centimeter signal? 2 types of observations are there to do this. One is that those observations that are done by interferometers, trying to probe the spatial fluctuations of the 21 centimeter line across the sky, either in a statistical fashion, looking at the power spectra, or potentially even making images in the future. And the other type of experiments are those that are done with a single antenna, where we try to look at this sky average 21 centimeter line, the same line I was showing you before. Right, so let's start with the interferometers. As I'm sure all of you are aware, with an interferometer we measure visibilities, and with those visibilities we can do an inverse Fourier transform, get an image of the sky. We can also do a Fourier transform alongside the frequency axis of the visibility and get the power spectrum of what we are observing. The interesting thing here is that if we do this, if we do a Fourier transform along the frequency axis, we see that everything that is smooth, of course, will appear at low K modes. And the foregrounds we expect to be much smoother than the cosmological signal. And this is the key here. This is what we are trying to use to separate the cosmological signal and the foregrounds. The fact that we expect the cosmological signal to be a lot more chromatic than the foregrounds. The foregrounds will appear here at the bottom of our power spectrum, and the cosmological signal potentially everywhere. In these simulations, you can actually see how the foregrounds tend to appear in the power spectrum, K perpendicular, K parallel modes. So these are spectral modes parallel to the line of sight, and spectral modes perpendicular to the line of sight. And as you can see, foregrounds are mostly there. You have 21 centimeter signal also at higher K modes. The idea is to clean the foregrounds until we can see the 21 centimeter signal, or potentially select the K modes where there is less contamination of the 21 centimeter signal. So let's look at this plot a little bit more. We have K perpendicular modes, perpendicular to the line of sight, proportional to the baseline length. So longer baselines will be measuring smaller spatial scales, so to the right of this plot. And then we have K parallel modes, which are proportional to delay, or the inverse of frequency. So smooth things appear here at the bottom, and very chromatic things, fast-changing things appear at the top. The foregrounds are smooth, although our instrument is not. And our instrument makes the intrinsic smooth foregrounds to leak into the top, the high K modes, creating what we know as the foreground wedge. So all of this yellow area is actually leakage, power leaked from the foregrounds into the EOR window, where we will be expecting to detect the 21 centimeter signal. There are two ways then to go about this. How do we avoid this foreground leakage? One way is to do foreground removal, and this is what LOFAR, for example, is doing, or what the SKJ will do in the future, which is to use many long baselines and a lot of sensitivity to measure the foregrounds, measure the leakage, clean it from your data, and then see the EOR signal, the 21 centimeter signal behind. The other alternative is that we don't need these long baselines. We stick to very short baselines, and we go to very high delay, so we need an instrument that is very spectrally smooth, not chromatic, and we try to find those K modes where we think the contamination is virtually nothing, and then look through those modes to see if we can find the 21 centimeter signal. That's what instruments like HERA, Hydrogen Epoch of Re-ionization Array, are trying. Now, the problem here is that to do this, we need, in both cases, high sensitivity, a wide frequency band that we need to Fourier transform, and short baselines, because really it's in the short baselines where we have a better chance to look at the EOR signal, even if we are cleaning some of these foregrounds. And the problem is that there are plenty of things that come with a telescope that has all of this in the form of coupling between antennas, reflections in the antenna itself, cables. All of these things are a subproduct of having a lot of sensitivity, a wide frequency band, and antennas very close together. And that is the challenge at the moment and the bottleneck in 21 centimeter experiments. One of the things we have found out recently is that mutual coupling between these antennas is actually one of the dominating systematics. We will be expecting to see again the foregrounds, intrinsic foregrounds at the bottom, and then some leakage as we go to higher K-perpendicular modes, but hopefully we're expecting to see a clean window here. However, all of this power comes from the coupling between the antennas in the array. And we need to bypass this, either by filtering it and even reduce further our EOR window, or design better instruments and try to make sure coupling is not a limiting factor. HERA is one of these instruments where Kavli has been very active on through different researchers over the past few years. HERA is already working, producing excellent science, as I will show in a moment, and we have been contributing to different aspects of the design of the system, of the data analysis, as well as in the interpretation of the results. And HERA is actually the interferometer that has the best upper limits in the power spectra of the 21 centimeter line. The latest one published in January this year, which are these orange squares. And as you can see, these are some fiducial predicted 21 centimeter models. It's still about an order of magnitude away, but we are getting closer. However, these systematics are tricky, and it's not clear when or how are we going to do this last push to get to the 21 centimeter signal, but it could happen at any point. Now let's move on a little bit and talk about what the future might bring, and that is the Square Kilometre Array, where we actually hope not only to be detecting the power spectra of the 21 centimeter line, but also to make images of the 21 centimeter line across the sky, because it will have the capabilities to make these images, the long baselines, the many baselines, and the super sensitivity that should allow us to do so. The SKJ is more than just a 21 centimeter cosmology machine. It's an observatory that will do a lot of different types of science, but the low frequency instrument in Western Australia is meant to be doing the 21 centimeter cosmology science case, and the predictions are that it was going to be almost an order of magnitude better than existing instruments to do the foreground removal, while it will be maybe not much better than HERA, or actually worse than the best predictions from HERA to do the foreground avoidance. Remember that for foreground avoidance, we need a lot of short baselines. We don't care that much about the long baselines. We need a very compact array, and that's it. SKJ is actually not meant to be doing that. It's meant to be cleaning the foregrounds by measuring them first. A lot of work on SKJ in Cambridge, as you might have heard in the past. We have people working on the development of the science data processor, the brains of the telescope, on designing the actual SKJ-1 low, this cosmic dawn EOR instrument, as well as in developing the tools for analyzing the data that is going to come out of the science data processor. Quite a few people involved with these activities, and these are some of the key people that are part of the efforts currently, and of course, please go and contact them if you want to know more about what's going on with the SKJ. Right, maybe before I go to the global signal, which is the last thing I'm going to talk about, the SKJ is actually not online yet, as you might imagine. It's going to be online probably by the end of this decade, right? So there is still quite a bit of work in development. I mentioned at the beginning that we have interferometers measuring the power spectrum, but also we have single antenna experiments measuring the sky average signal. And this is where we have a strong presence in Kavli in these global experiments, but also where the best results to date have been published. Experiment by the name of EDGES in 2018, which again a lot of you might have heard about, published a result that was not predicted of a potential detection of this dip at the cosmic dawn that I saw before, 78 megahertz, which will have really fundamental implications if it was to be true. Because it means that we will be below this line, which is what the CDM model will predict for the cooling of the gas. So in this axis we have the ratio between the spin temperature and the background temperature, and this is a CDM model of gas cooling. And EDGES put this point there, which means that either the background is hotter than expected, or the gas is colder than expected, or there is something else, like some sort of systematic distortion. Plenty of papers have been written to dig into, or to dip into all of these possibilities. We have written quite a few papers also about the potential of systematic distortions, and members of the Kavli have written several papers where we describe how this point actually could just be some observational bias. Right, let me move on, because I think we are getting close to the point when I need to hand over to Anastasia. So there is a project we've been leading from the Kavli for the last 4 years that is about to start observations, called REACH, in which we are taking a slightly different experimental approach compared to other experiments. Mostly, as you might have gathered up to now, we have 3 components in our signal: the average foregrounds, the smooth foregrounds, the cosmological signal, and whatever is introduced by our instrument. Most experiments until now, global experiments using a single antenna, have assumed that this is pretty much non-existent. They have done a very good design, so this is very flat. They have constrained the frequency band. They have designed antennas and systems that don't have much of this, or so they think. We don't think that's possible, so we have taken a different approach in which we don't assume this is gone. Of course, if we can have it gone, it's great, but the most important thing is we have designed a system that hopefully allows us to disentangle this from the other 2. So how have we done this? Several things that I will have to go fairly quick through them. Mostly we have developed a full Bayesian analysis pipeline where we can actually get the relevant information to understand the degeneracies between these 3 parameter spaces: the foregrounds, the cosmological signal, and the instrumental power. We also have 2 different antennas rather than 1 observing simultaneously. Both of them seeing the same foreground, seeing the same cosmological signal, but with very different instrumental effects, which hopefully will allow us to disentangle these effects. We've been trying on training our pipelines with different types of data, showing that this approach is actually working fairly well when compared with the standard approach used by instruments until now, in which foregrounds were assumed to be smooth and not very much affected by systematics. And we have been, until now, working on the development of our antennas, of our system, and trying to understand how our approach will improve over existing experiments. One thing I would like to mention before I finish this part is that the receiver, the hardware of the REACH system also has quite a few upgrades compared to existing instruments. We, for example, monitor and measure all the components in the receiver box in the field continuously, rather than relying on measurements that were done in the lab in the past. So we are a lot more protected against changes in our system. We are international collaboration in REACH, and we have plenty of people behind all this work. Some of them here in the Kavli, you will recognize some of the faces. For example, Will Hanley, if you want to know more about the data analysis, go and talk to him, or Anastasia, if you want to know more about the theory. We have 22 people in Cambridge, and more than, well, actually 20 research students and early career PDRAs, which is really our force here that is actually moving REACH forward. Okay, so I think I'm gonna probably just quickly go through this now. So we are about to start observations in a couple of months with REACH, and it's not the end of the story. We are already making plans for the future, which will be radio astronomy from space, so that we can actually go to the higher redshifts of the dark ages, which are completely obscure from the ground. And we have a project called CosmoCube that we are starting to develop now, in which we will have a satellite orbiting the moon, making observations from the far side of the moon, and then trying to detect the 21 centimeter signal all the way to about 5 million years after the Big Bang. Right, so I was going to tell you a little bit about synergies, but I think I need to hang over now, and Anastasia is going to tell you some about the synergies between 21 centimeter signals and things like galaxy observations, which we've been doing some work about. So I want to leave you with this, which is actually the best results to date of 21 centimeter observations, leaving aside the edges observation until it can be confirmed. Measurements of the power spectra by HERA, measurements of the global signal by SARAS have been combined by researchers, students, and postdocs in the Kavli to produce the best constraint of astrophysics at the cosmic dawn using the 21 centimeter line. And with this, I would like to hand over to Anastasia so she can tell you more about how to make sense of all of this.
Okay, can you hear me? So I'll be talking about theory and interpretation, taken over from Eloy. And one thing to realize is that 21 centimeters, as any intensity mapping probe, actually is sensitive to the typical population of galaxies. So unlike JWST or X-ray surveys, for example, that pick up the brightest sources, it is sensitive to the most typical galaxies that contribute the most amount of photons. So there are, as Eloy described, we are working with different types of experiments that are attempting to probe this typical population of high redshift galaxies, especially at cosmic dawn and reionization. However, it's not the only experiment, of course, that is looking at the early universe. There is JWST and even Chandra, and gravitational wave detectors are trying to measure population 3 and high redshift galaxies. And so one of the main interests here at Kavli is to actually use these synergies to completely characterize the high redshift population, starting from the very first stars produced maybe at redshift of 30 and going all the way to the end of the epoch of re-ionization. So we're trying to foster the synergies here and build the best possible models to address both the 21 centimeter signal, that is very large scale probe of the typical galaxies, and also include sources that can be detected by JWST and Chandra. So as Eloy showed, there are no confirmed detections yet. There are only upper limits that are rather weak still. So at the moment, we are mostly using this model that is kind of a bit extreme. And that was first brought to explain edges, but of course it's more varied. So we can get deeper signals than what we expect in standard astrophysical scenarios by boosting radio background. It can be either a contribution of radio galaxies at high redshifts, or more exotic sources such as superconducting cosmic strings or dark matter annihilation, or maybe neutrino. So Eloy gave background of the signal. I'm not giving that, but a deeper signals than expected can be produced if you either boost radio background by these exotic sources, or if you cool gas temperature, for example, by introducing interactions of baryons with dark matter. And we explored both of these scenarios. So I will be showing you inference related to this type of models where signals are much deeper than expected. And that's what we can do with current data, probing these extreme scenarios. So we use these models to test our pipelines, see how well data can be constrained by these models, and also provide first constraints on the population 3 and cosmic dawn galaxies. So this model contains a population of galaxies, for example, model presented here, that are formed at already redshifts starting at redshift 60 and 50 with the first galaxy populations. And they contain X-ray sources such as X-ray binaries, but also produce radio emission and Lyman alpha and Lyman Warner photons, so to create 21 centimeter signals. If one includes radio galaxy at high redshifts, then this 21 centimeter coupled bubbles, coupled by the Lyman alpha radiation produced by the first stars, would be much brighter in the centers of the galaxies, with radiation getting dimmer as we go to the outskirts. And so such galaxies could be probed by the SK in the future easier than if we don't have these radio populations. So when we add radio emission to galaxies, we can create deep absorption, such as produced by edges, for example, explain the deep absorption trough. But we never get this flattened emission, flattened absorption troughs, which require a bit more physics. And I'll show you at the end of my talk how these flattened profiles can, in principle, be obtained. But in these models where we have extra radio emission by galaxies, we also boost power spectra, which gives us extra handle on constraining these models with, for example, if such enhancement is observed by NANUFAR or HERA or SK in the future. So there is always consistent boost in the power spectrum that we can test. And this class of models is, as I mentioned, very convenient because we can already start ruling them out or testing them with existing data, which is otherwise weak for constraining more standard models where there is only radio background produced by the as a cosmic microwave background radiation. So thanks to this boost in radio, we produce very deep absorption signals that can be ruled out by instruments such as SARAS-2 and SARAS-3. And Harry did look at constraining this model. So he created the pipeline, the full Bayesian inference, including systematic variations and also marginalizing over foregrounds. And so with this code that Harry created, we can rule out the most deep absorption. So here in blue, you see the whole prior of global 21 centimeter signals from these models. And in the red is the posterior after we apply SARAS-3 data constraints. So SARAS-3 is an instrument sensitive to very high redshift, so probing 21 centimeter between redshift 15 and 25. So actually, it's one of the first instruments targeting directly cosmic dawn 21 centimeter signals. And we see that this prior shrinks a lot in the very high redshifts of cosmic dawn, thanks to constraints, thanks to the data provided by SARAS-3. SARAS collaboration is an Indian group that placed this antenna in the water, not far from actually Bangalore, where during the pandemic, this zone was radio quiet, so they got the best existing limits on the cosmic dawn 21 centimeter signal. They also have another instrument called SARAS-2, which is more sensitive to Epoch of Re-ionization signals. And with SARAS-2, we can constrain signals around redshift 6 to 12. And we see this green is the posterior of signals after we propagate them through the SARAS-2 sensitivities. So both SARAS-2 and SARAS-3 provide unique constraints on this type of models, and they're sensitive in different frequency ranges. So thanks to Harris pipeline, we can constrain 21 centimeter in 2 different redshift bins independently, and then get joint constraints. So this is one example of synergies where 2 different instruments can be used in 2 different frequency bands, constraining the same type of the same model without needing to extrapolate. So we can, with this pipeline, we can start placing first limits on actually properties of galaxies. Of course, it's model dependent, but within this model, we can constrain star formation, X-ray heating efficiency, and radio background strength of these models. And we see that SARAS-3 here. So first of all, they didn't find a signal reported by edges, even though some of the edges motivated models are still consistent with the data. But within this non-detection of models, we can rule out enough signals to start informing ourselves about the properties of the very first galaxies. So in particular, this data was sensitive to star formation efficiency of the first stars and the minimum circular velocity of first halos, which is just proportional to halo sizes. So we can start constraining how first halos, how massive were the first halos, how efficiently they form stars, and also what was radio efficiency of these galaxies. So of course, these constraints are pretty weak even for these exotic models, but as I said, it's the first ever attempt to constrain galaxies at redshift 20 directly. We also did a similar exercise, but using HERA upper limit. So Eloy introduced HERA, and the data of HERA is still very weakly constraining standard astrophysical scenarios where we don't have this boost from radio galaxies. So it's this black line here, which gives us upper limit on these possible models with the CMB as a background radiation. But as soon as we boost background radiation slightly, 21 centimeter is more intense, and these models are above the upper limits reported by HERA, so we can start ruling them out. And that's work done by Stefan here at the IOA. So he was a very active member of HERA collaboration, coming up with likelihood prescriptions and doing one of the first analysis to constrain power spectra, to constrain parameters of galaxies at reionization using HERA data. So it turns out that HERA is actually complementary to other surveys. So for example, Chandra X-ray satellite provides observations of X-rays, of course, and there is a portion of X-ray emission that is not attributed to any sources, so it's unresolved. And one of the explanations for this unresolved X-ray background could be that it comes from very high redshifts, and it's a kind of emission of the first galaxies accumulated that reaches us. So this X-ray emission would be sensitive to a combination of star formation efficiency and X-ray production efficiency of these first galaxies. And so Chandra X-ray background would rule out very efficient galaxies at high redshift, so this portion of our parameter space. On the other hand, there is also a measurement of radio background directly produced by RK2 and LWA, and this gives us an upper limit on how first galaxies can be efficient in directly producing radio emission. So this would be sensitive to our star formation efficiency and radioluminosity of a galaxy. So the existence of LWA measurement actually rules out super intense galaxies at high redshifts in terms of radio emission, so ruling out this part of the parameter space. And it turns out that through 21 centimeter emission, we are actually sensitive to the complementary part of the parameter space, excluding very efficient radio galaxies and very inefficient X-ray emitters, which would contribute to the very intense 21 centimeter signals. So already now, the HERA is providing very interesting limits on these models, which are the exotic. So with improving data, we would be able to say very interesting things about radio emission and X-ray emission and star formation of these first galaxies. We also did the very first synergy in the world between a global experiment. In this case, we used Saros-3 data. Again, this work was done by Harry, and Irena and Stefan contributed, and a bunch of other people at KICC. So this is really the first ever attempt to constrain models using different types of radio experiments, global signal experiment measuring the total power in the signal and the power spectrum, and an interferometer measuring the power spectrum at different redshift ranges. So HERA measures 21 centimeter at redshift 8 and 10. And Saros-3, as I mentioned, is focusing on redshifts 15 to 25, so probing cosmic dawn signals. So Harry wrote a code called margarine that can put together different types of data, marginalize over unnecessary parameters. And with that code, I'm sure he can tell you much more about it if you're interested. So I intentionally didn't put enough details, so you can talk to him directly. He's here. So with that code, we were able to look at both power spectra and global signals and constrain models along two different directions. So this again shows the prior of global signal and power spectra that we have in our model, and then how it's constrained independently through Saros-3 and HERA observations. And we see that both of them contribute to our constraints on the signals. And the Eloy flashed this plot, so let me explain it a bit more. So here we have a spin temperature over radio background temperature. That's one of the basic quantities that we calculate for 21 centimeter signal as a function of redshift. And we have, in gray, the constraints from Saros-3, and in blue, the constraints from HERA. And we see that depending on redshift, at specific redshift range, HERA dominates here at low redshifts where it pins down the models. But because we have a model-dependent inference, HERA constraints actually go all the way to high redshift. So we can learn about models, about cosmic dawn signals using HERA at redshift 8 already. But we don't need to do that because Saros-3 provides independent constraints on much higher redshift, so directly at cosmic dawn. So we have limits from a cosmic dawn observation experiment. And using Harry's margarine, we can pin down these models both at low redshifts and high redshifts together. So this analysis allowed us to put the best existing constraints on the radioluminosity and X-ray efficiency of the galaxies throughout cosmic history, actually. So again, we expect these constraints to improve and this method to become more and more useful as there is more data and of better quality. So we are actually working further on this, and Simon, who is also in the audience, is putting everything together. So we also included Chandra limits through the same margarine pipeline to have constraints directly on the likelihood of X-ray emission. So here you can see it better, but I'll switch back because I need the legend. So, and this model actually is a bit more involved because it has population 3 star formation that I will be talking in a second, and graduate transition to population 2. So we have 2 parameters to constrain about star formation efficiency here. Population 2 star formation efficiency on the left, and then the next one is star formation efficiency of directly population 3 halo stars, so the very first stars formed at very high redshifts. And with HERA only, we find that actually, or with all these tracers, we find that actually we do have quite a bit of sensitivity constraint in population 2 stars, dominated by constraints from HERA at redshift 8, but population 3 are still very weakly constrained. So even with Saros, we don't have enough sensitivity to start constraining population 3. However, one of the most interesting constraints, as I wanted to point out, comes from X-ray efficiency, and we see here that HERA, this orange line, constrains very low X-ray luminosities because that's what contributes to very deep absorptions or strong power spectra. While Chandra, for example, X-ray background from Chandra would constrain very strong X-ray galaxies, and so we start obtaining this emergent picture of measuring actually X-ray efficiency of high redshift galaxies from both sides. So it's not just upper limits, it's whole, we start obtaining the whole PDF. So eventually the hope is to have very narrow constraint on this X-ray efficiency of first X-ray binaries through a combination of probes. And of course JWST is the big next big thing existing that we want to make use of to constrain high redshift galaxies, and Jiten, he's a first-year student, started working on introducing constraints from JWST into the 21 centimeter pipeline, and the hope is to directly constrain luminosity of EOR galaxies and then develop synergy with 21 centimeter signal. So, don't know how much time do I have. Who is running the show? 15? Okay. So, sorry? 10. Okay, fair. So I showed you the very first ever constraints on the population of early galaxies, but how do we actually model this population and what actually 21 centimeter can tell us about these galaxies? So we do have power to constrain them, and again, the main thing to realize is that 21 centimeter is a large-scale probe. It doesn't probe individual galaxies, but it will give us information about the statistical properties of the population. And it's a tomographic scan of the universe, so we will get this information at every redshift separately. We can see how the statistical description of galaxies evolves with redshift and time, with time and scale. So we need to model that effectively, but we cannot really resolve galaxies, so there is no point in really putting a lot of computational power into resolving small-scale sources. So 21 centimeter is a sensitive probe of a bunch of stuff, and this is an example of a light cone, so evolving from dark ages when there were no sources yet, and through the cosmic dawn when first stars started producing Lyman alpha radiation, and first X-ray binaries formed, heating up the gas slowly through the end of the epoch of Re-ionization, when all the gas became ionized by more massive galaxies. So this is a rich picture, and on one hand side, we want to create a flexible theoretical model that can explore variations in this astrophysical scenario, so we don't know what properties of the sources were. But we also wanted to be accurate enough to represent possible reality. So Eloy introduced that, but I just want to remind you that 21 centimeter is first sensitive, of course, to amount of neutral hydrogen, how neutral is the universe. And this fraction is mostly close to 1 through the whole cosmic history and drops very sharply when more massive galaxies emerge and start ionizing the gas. It's sensitive to the radio background, as I already told you. Gas temperature that varies as a function of redshift. Since I introduced that, I will just briefly tell you that gas cools down as the universe expands, but as soon as we have some sources, for example, X-ray sources, or that hit the gas, or Lyman alpha photons can also hit the gas through collisions and scattering. So this temperature starts raising up, and eventually gas is hotter than the background radiation. But one of the main players is the Lyman alpha emission that actually couples the 21 centimeter line to the gas temperature in the first place. And so thanks to this effect, we have observable signals. So we need to model all these ingredients. And one topic particularly that we are interested in in the recently is addressing the question of the first stars, so the very first population of stars, how big they were, when they formed, what was the initial mass function. And we recently had a visit by Ralph Klesen here, who told us a lot about population 3 stars. And one thing he told us is that the initial mass function of the stars is very unconstrained still. There are many groups trying to simulate it from and explore what is the distribution of stellar masses of zero metallicity stars. So the very first stars formed from hydrogen mostly. But there is no convergence. Different groups report different results with masses that can be as small as 10 to the minus 2 of solar mass to 1,000 solar masses, so huge stars. And these stars will have different properties in their luminosities in UV and so various bands. And this luminosity can affect 21 centimeter signal in different ways. So that's what we're trying to explore now with Thomas, who is also in the audience. And if you have any questions, I invite you to talk to him about that in more details. But Thomas did a very thorough job in addressing the question of how the first population of stars would affect 21 centimeter signal, and how the signature depends on the initial mass function, so on the size of the stars. So Thomas did actually explore evolutionary tracks of zero metallicity stars, so the very first population using MESA. And then he calculated SEDs, so emission of the stars using a stellar atmosphere called +T. And previously in the field, before Thomas started, everyone and still, except for our group, everyone is using this black body approximation that is this orange line here. But the blue line shows the true SED that we get with the stellar atmospheres code, with lines and so on. So it's quite different. And these differences can actually be seen in the 21 centimeter signal. So one of the key things that Thomas found is actually through this difference in emission and also lifetimes of the stars, is that 21 centimeter signal can be sensitive to the mass of the stars if they are lighter than 20 solar masses. So such stars would live much longer, and their emission would be different from what we expect from very massive stars. If all stars, the first stars are very massive, and the initial mass function is top heavy, then we won't see any difference because all the stars live quite short times and produce similar luminosities. This, however, only includes the effect of first stars on 21 centimeter signals through Lyman band effects, such as Lyman alpha coupling, Lyman alpha heating, and Wolf-Thousand field effect. So here we didn't include any contribution to heating from X-ray binaries. And we do expect these different initial mass functions to produce different populations of X-ray binaries. So that's one of the works in preparation, where Thomas also includes X-ray binary population, and we see way different signatures from population 3 stars through Lambda effects and X-rays, propagating all the way to actually the epoch of re-ionization. So stay tuned and look out for this paper coming, hopefully soon. So this is to give you a bit more details. We explored 4 different IMFs from saltpeter, that is close to present day stars, to a very top heavy flat IMF. And this is the emission of photon emission rates of stellar populations in the case of different IMFs. So they look quite differently, and that's what imprints signatures in the 21 centimeter signal. We also include gradual transition from population 3, so zero metallicity stars, to population 2, which are more metal rich, through a prescription that includes supernovae explosions. So in different, so first stars were presumably massive and exploded soon after their birth in energetic supernovae, expelling gas from first star-forming halos. And then it takes for gas time to recollapse and start star formation as population 2 stars. And depending on this delay in recollapse, we would get different signatures in 21 centimeter power spectrum and global signal. And so we see that the signal is sensitive to this transition between population 2 and 3 stars. And potentially this transition can be measured. We still haven't explored in detail how degenerate is this recollapse time from other parameters, so that's another work that we need to do. And the most recent thing that Thomas did was to look at heating of the intergalactic medium. So I so far described heating by X-ray binaries that would heat up the gas on large cosmological scales, but there are different other sources of heating, and one of them discussed in literature is cosmic rays. Same supernovae that initiate transition between population 3 to population 2 stars would also produce cosmic rays that can heat up the gas more or less efficiently. And the efficiency of this heating depends on the magnetic fields, how fast these cosmic rays are accelerated. And there are 11 orders of magnitude uncertainty in primordial magnetic fields. So that would translate in uncertainty in how efficient cosmic rays can be. So we looked at different types of scenarios. And again, I invite you to talk more to Thomas if you want to know the details. But the idea is that cosmic rays, in any case, even in the most efficient case, they cannot propagate far into the IGM. So all heating that is created by cosmic rays would be very local and very different from what we expect to see in the case of X-ray heating, for example. So Thomas explored several scenarios. For example, when cosmic rays are locally confined, so if they cannot escape too far from their host halos, compared to the case when they move as far as they can. And in both cases, they can only move just a few. So even in the most optimistic case, they can move only a few megaparsecs, injecting all their energy very close to the source. And this is very different to what we expect in the case of X-ray sources. Even in the most soft X-ray source scenarios, these photons would propagate tens and hundreds megaparsecs, heating up the gas on much larger cosmological scales. So this different type of heating can be seen in 21 centimeter maps, as we see here on the bottom. So cosmic rays versus X-ray heating. And hopefully with 21 centimeter tomographic scans, such as with the SK, we can directly see if heating was confined or on much larger scales, and we can establish what was the main heating mechanism at high redshifts. So once we get this new heating mechanism, actually our thermal history becomes way more interesting than the one I showed you at the beginning. So I showed you that we had gas cooling down adiabatically with the expansion of the universe, and then when X-ray heating sources kick in, gas warms up. And that was compared to the radio background. So for example, CMB cooling down with the expansion of the universe. But once we get another heating term, this thermal history becomes modified, and it can be very interesting. So in some of the models that Thomas explored, gas, for example, these top panels show cosmic gas temperature. So there are wiggles and minima, local minimum and maxima, because there is competition between different heating scenarios. So in this particular case, we didn't have X-rays at all. There was only competition between the adiabatic cooling, cosmic ray heating, and heating by lambda alpha photons, which are produced in models where we have stars anyway. So if there is in this scenario, there is a minimum halo mass of stars, of halos that form stars, but there is a maximum halo mass of halos from which cosmic rays can escape. So the interplay between these different thresholds for star formation and for cosmic ray escape creates this interesting thermal histories. So this leads also, as a result, to non-trivial 21 centimeter shapes for global signal, and a bit also imprinted in the power spectra. So something interesting to look for. And in particular, if one plays with this halo mass from which cosmic rays can escape, we can create histories like this black line that create flattened 21 centimeter absorption, which is remarkably similar to what edges sees in shape. We don't claim that it explains edges by no means, but it's just curious that we can create this flattened absorption profiles by playing with heating scenarios. Here the amplitude is still not as deep as edges sees because we don't have any extra radio background in these models, but by tuning or by playing with different heating terms, we can modify the shape of the global signal. Okay, I would just say that we also put a lot of effort in modeling X-rays. Nina looked at population 3 X-ray binaries, and Boyan now continuing this work modeling X-ray binaries, and that could potentially link to gravitational waves because these binaries would also create gravitational waves. And I'll stop here with my conclusion. So I hope we both showed you that a new window to the infant universe is about to open up. And we will have exciting probes of early star formation, X-ray binary population, possibly gravitational wave sources through 21 centimeter signal. There is a rich ground for synergies with various telescopes, including in between 21 centimeter probes, interferometry and global signals, and also for other bands such as X-rays, UV with JWST and radio. And the KICC is really an excellent, we have an excellent team working on various aspects of this field, from experiments, instrumentation, observations, and theory and interpretation. Thank you.